Okay guys, so we will start the next reading, which is again going to be module 3, and let's start with a very interesting reading. It is more conceptual rather than getting into the details of the mathematics and other things, which was a lot in module number 2. But yeah, coming to module 3, what we are going to talk about today is about how is the bias introduced in the very first place. Okay, so it's a kind of a reading which GARP expects you to understand, and it calls out what could be the sources of bias. Okay, rather than talking about the placement of the sources, it says that whenever you develop a piece of a software, because most of your machine learning AI is going to go through the software development life cycle, and in the software development life cycle there is going to be requirement analysis. Okay, so what happens in requirement analysis is that a set of business users or a set of people who are eventually going to use the software are going to give you the expectations, the requirements from what they are trying to build. Okay, and then the second thing is going to be about the data collection, you can say, or you can talk about the acquisition of data, because most of your machine learning AI is going to be heavily dependent on data, whether you use supervised, unsupervised, reinforcement, whatever. Then it is going to be your model development. Somebody is going to write the code, somebody is going to decide which algorithm to use, supervised, unsupervised, etc., and the final thing is going to be your model deployment. Okay, so it is going to be deployed on some kind of an infrastructure, and then people will slowly start using it. So we'll go through these things one by one, and I'll not get into too many details because that is going to make it more and more complex. But let me tell you, let's go one by one. Let's see how long it takes. So let's start with the requirement analysis phase, or the problem specifications, you may call it. Now what happens, I work for as I told you earlier, I work for a large consulting firm, and if tomorrow we need to hire, okay, if I need to hire an analyst, if I need to hire an analyst in my team, and I need to write some kind of a JD for it. When I say JD, it's a kind of a job description. Okay, because of my background, because of my research, because of my PhD, my job description is going to be more aligned with things like, he needs to have because I'm hiring an analyst, I will say that his math needs to be very good. He needs to be a good programmer. Okay, so those are the specifications that I may put in my job description draft. Now if I give the same work to somebody else in my team and ask him to write the JD, and let's suppose there is a person X in my team who has done his or her MBA, and he or she is engaged with clients around design thinking and those kinds of things, then their definition of this job description might be more to do so with the intensity of domain. Okay, so they may say that if I'm hiring an analyst, the person needs to understand the industry, whether it is retail, manufacturing, financial services, etc. So net the point that we want to derive is that the definition of the problem itself can create a bias in the first place. So that's part A, and now let's suppose we have the JD in the first place. Okay, whether it is by myself, which is more math intensive, or by somebody else, which is going to be more domain intensive. But let's assume that we have the JD in the first place. Now you have the JD and you get couple of CVs. Now if I say that the intensity of domain needs to be high, how do you measure the intensity of domain? So let's suppose this is your requirement when. How do you measure requirement when looking at these CVs? Whether it is manually, whether it is algorithmically. So if you say that your experience on a particular industry could be the reason that if you have worked 5 years for an oil company, which means that your domain experience on that oil company is good. Okay, somebody has an experience of say 3 years, or somebody with an experience of 1 year, we can sort them that this person is going to be more domain, he's going to be more intelligent on this domain, which is again a kind of not so right always, because people can spend more time. There can be people who can take time off for whatever reasons, and their number of years, if it says that from 2021 to 2025 people may have taken time off, etc., etc. So the measurement of the requirement with the metric itself can be flawed. Okay, which is also the part of the part of the entire problem specification itself. Okay, so that's one thing. Then the second is the second issue in specification is, it's called GARP. I'll use the same words which GARP is saying. It says fairness through unawareness. Okay, so this is exactly what GARP is calling it out, and again a part of problem specifications itself. But what they want to say is that there are regulations everywhere, regulations in the Europe, regulations in the US, which says that let's suppose you want to create a legal app. Okay, and this legal app is going to give some kind of an input to the judge or whosoever that is going to decide whether the person X is going to be granted bail or not. Okay, so now one of the very important criteria for anybody to grant the bail or not grant to the bail is that they tend to measure an indicator called as FTA. FTA stands for fail to appear. What it means is that if I grant bail to person X and this person X absconds and he does not appear in the next hearing, then it's a threat to the community, to the society, so it's better that we do not grant that bail. Now how do we compute this fail to appear parameter? Okay, so your legal app is going to give you some kind of an indicator of fail to appear, probably say on a scale of 0 to 1. So if the person is 90% probable fail to appear, then you probably can deny his bail, but if he is 10% fail to appear, you can grant his bail. Now how this algorithm may work, let's suppose you create a kind of a regression algorithm which says some beta naught plus beta 1 on parameter 1 and beta 2 and parameter 2. Now you assume that let's suppose this parameter 1 is your criminal history. Okay, so if somebody has been engaged into crimes historically, then there is large likelihood that he may fail to appear. And let's suppose your parameter 2 is some kind of race or ethnicity. Okay, because again it's all data related things, we may personally agree, disagree to few things, but if the data says that people from a particular race or community or ethnicity are more likely to get absconded, then those kinds of parameters may also get embedded into this regression equation. And let's suppose just hypothetically, let's suppose this is 0.1 and this becomes your 0.6. okay, and let me call it as criminal history, and I'm saying this is as your 0.3 of your race. So that's how we are trying to compute. Now if your regulations and and lawmakers or legalities they force you that you cannot use race as a parameter. Okay, now you cannot use race as a parameter in your equation. Okay, so what will happen in most of the scenarios is that you will say, okay, let's create this by calling it as gamma naught plus gamma 1 into parameter 1. Let's get away from P2 in the first place. So that's the that's the general consensus, of most people, that okay, let's get away from P2 itself. But imagine that P1 and P2 might be correlated with each other. Okay, what this means is that your higher P1 and P2 can be correlated with each other, in which case what will happen is that your gamma naught will nothing be but your earlier beta naught, plus it will be some kind of a combination of your correlation of your P1 and P2 and some, let's suppose you use maybe alpha something, and your this gamma 1 will nothing be but your beta 1 plus some kind of a correlation between P1 and P2 and multiply by P1. So you are actually not eliminating P2 entirely and finding because these parameters, while we said that in multiple algorithms or in supervised unsupervised regressions, the parameters should be independent of each other, but that's not how the real world operates. So you may come up with say 0.2 plus 0.8 of say parameter 1, okay, which makes it highly dependent on parameter 1, and the person who you are trying to protect by not using equation 1 is also not going to be protected by using equation 2. So the it's and that's why it's called fairness, fairness through unawareness. So even though we are unaware and we feel that we have eliminated P2, but we have actually not eliminated P2. So that's the brief about the first part, which is creating biases because of the problems with the problem definition of problem specification itself. Let's come to the second part of software engineering, which is more to do so with data collection. Okay, data collection is very important, and your algorithm is as good as your data that feeds into it. Okay, so the first problem when you are 2.1 is kind of historical bias. So what happens that let's suppose you want to create any algorithm which let's suppose you want to create an algorithm which tells about again a kind of a job thing, which says whether a person or who you are going to use a CV only for that reason, and it is fit for a particular role or not. Okay, now let's suppose you want to hire for a doctor. Okay, and you want to hire for a doctor of, say, let's suppose heart doctor. Now, and how do you create this algorithm? You go through all the doctors that you have been in the history, and then you try to find out who have been the good doctors, and then you see, okay, what are the behavioral similarities of all the good doctors, and that's how you create a algorithm for finding a good doctor. And then once you pass this new CV via that algorithm A, it gives you the goodness of that particular CV in terms of how well that doctor is going to be turning up. Now the problem with this approach is that historically you may have seen that say 90% of the doctors in the past could be males, okay, and only 10% females. Forget about transgender, they will be probably in decimals or not even decimals. So now the problem with this is that it is going to give a preferential treatment to males. Not just a preferential treatment, it is going to exaggerate that or amplify that even further. Okay, so that's the first problem. It's also called as the feedback loop, or some kind of a bias getting fed into the algorithm as a feedback, and then the algorithm becoming even more unfair for females in this case, and creating a problem. So that's the historical bias. Okay, the second problem is so I hope you're clear about historical bias, is about the collection in the first place itself. Okay, now the most of the machine learning or the research or all this AI etc. is being focused mostly in the Western world. When I say Western world, this means US plus Europe. So most of the data that is available, or most of the algorithms that are free to use, and this applies to even the right now state of the art LLMs, Gen AI, whatnot, they have used the data mostly from North America and EU. So let's suppose you want to do a face recognition algorithm. This face recognition algorithm, even today, most of the state-of-the-art face recognition algorithm will give you a very good accuracy for white people, but it will give you a bad accuracy for black people. Why? Because the distribution of data, or the way the algorithm is trained, it doesn't have the true representation of the other communities. Similarly, if you try to do some kind of an NLP or some kind of a text transformer kind of an algorithm, you will see that 80 to 90% of the data or training has been happening on English only. And maybe if you talk about Hindi, or if you talk about any remote language in India, let's suppose you want to talk about Tulu, it's only maybe 0.01%. Okay, so which means that if I try to use the same API to process a Tulu kind of language, and assuming the script is the same as Kannada or whatever, which it is able to understand, the processing capabilities are not going to be good. So the distribution of data in itself is a problem. Okay, this second problem, and this is more of the collection issue, and the third issue is probably, I'll say, representation. Now what happens that there are, when you collect data, okay, the representation is that, let's suppose the data contains three categories of or multiple categories, category 1, category 2 to say category n. Okay, and the distribution of data across these categories needs to be the true representation of those categories. Let's suppose we are taking some kind of a text data, and then there are, let's stick to only 22 scheduled languages in India, and we say that okay, the distribution of people in India across those 22 scheduled language is, let's suppose 0.4% is Hindi, then is Bengali is 0.1%, then is probably Marathi is 0.1%, and so on and so forth. Okay, so we say that this is how the distribution of people who speak these languages is based. So if we are creating 1 million, 1 billion, 1 trillion sentences, then this is how this is going to be. This is how these sentences are going to be distributed across those languages. So that takes care about the representation bias, but when we talk about that takes care of the collection bias, but then there can be scenarios where this may also not work. Let me give you an example. Let's suppose you want to create some kind of a medical diagnosis app. Okay, and this medical diagnosis app is, let's suppose the input to this is some kind of blood reports. Okay, and based on the blood reports, it is going to analyze these blood reports and give you some kind of an output, or some kind of a recommendation that this is what you should do, or supplements, etc. Now in scenarios where some women is, let's suppose there is a pregnant women. For pregnant women, the general cases of what parameters the blood report will represent may not be the same as what a non-pregnant woman or a man would mean that. Some of the parameters, I'm not a medical expert, so I cannot give examples of what goes up and down, but there can be some hormones differences while somebody is in their first, second, third trimester, and the parameters are up and down, and the analysis is going to be very, very wrong. Okay, so this means that even if you represent this in the same proportion, pregnant women, out of 100 samples that you take, there can be 3 or 4 women which will be pregnant, in a population. So even if you take 3 to 4% pregnant women's data and 96 to 97% other people's data, in the final model this will get very, very diluted. Okay, so what should we do in this case? There are multiple. I will not get into the solutions in the first place, because this reading is more about the sources of bias and problems getting into the models. But one thing can be that you create an independent model for this particular community. Okay, or you try to balance this data set in such a manner that it becomes 50-50 or 40-60, and then there are ways and methods to increase this 3 to 4% to 50%, whether it is synthetic data, whether it is some kind of bootstrapping, etc. Okay, but now the modern means are like, you use MOE kinds of model, which is like mixture of experts, and then based on when you get some kind of the input, then your first level is to see which expert you want to, when I say mixture of experts, this means that there are more than one models, and you have first model which is called as a selection model, and then you have various models. Okay, so if it is for a pregnant person, maybe M1 is for a pregnant person, and then M2 is for something else. So you first select which model it should be used, and then do that. So that's how these kinds of biases can be solved. Okay, now from data, let's move to third part, which is on the development side. MODEL, model development. Now assume there is the problem specifications are written, the data is also in place, and we have taken care of everything and everything. When somebody, so this is a place where a software developer or a mathematician or somebody, a statistician, etc., is trying to actually build the model. Now in this place, the problems that can occur is one is with respect to the choice of the algorithm, okay, and the second could be with respect to the parameters or the hyperparameters that the person is going to use, or in fact there can be problems with some of the APIs that the person is going to use. Okay, for example, in case of NLP, you'll see a lot of times I will go back to NLP for example, because that has been my area of PhD, etc. But in NLP, especially the earlier methods of converting text to vectors, we have spoken about this at length in our NLP session. But the word embeddings is a function of how the majority of words occur in the neighborhood of each other. So if I say a man or a doc, probably I'll say a doctor is to a man, and I'll say a nurse is to and then I say, okay, what is it? It will say it is a woman. Okay, so this kind of sexual biases is embedded in majority of text. This is how embeddings are created. So the choice of API, the choice of algorithm can also create issues. Okay, so what kind of API to be used, what kind of model to be used. Let me come to number 4 also, because number 4 and number 3 are kind of correlated to each other. The number 4 is model deployment. And what model deployment means, that if somebody, like most of these days the models are built by giants like Google and Facebook and most of these people, and so I don't know whether you have heard, there is a API these days from Google. It's called Google Perspective API. Okay, and this Google Perspective API, what this does is that it people can tweet some things, or people can put things on Facebook, etc., and you run this via Perspective API. So it is going to give you the toxicity of that tweet, the sexual suggestiveness of that tweet, the respectfulness, or if it is hate or not that hate, etc., etc. Now most of these elements are not just universal. Okay, there is a social, there is a cultural, there is a geographical, or maybe religious also affinity to this. So what may sound hateful to somebody in Norway may not sound hateful to, say, somebody in Middle East. Okay, versus to somebody in India. Okay, in India people tend to talk louder, people tend to talk in higher pitches, and people tend to speak over each other. But in Europe or anywhere, that's not the case. So if the model is designed for a particular language, for a particular culture, for a particular geography, for a particular context, and if we are trying to use the same model for a different context, it is not going to give you the same kinds of results. Okay, so this is the problem with model deployment, And the same thing I was also talking about model development, because the choice of the algorithm needs to be more holistic. You need to read papers and see whether the algorithm has been, or the API has been used in that context or not, whether you need to fine tune that algorithm so that it becomes relevant for your context, or maybe you need to outrightly reject that algorithm because otherwise it's going to be highly inaccurate. Okay, so that takes us to the end of this reading, which is about the sources of bias in module number 3.